Welcome to Multiphase System, Part 3, where in this Part 3, we will look into gas-liquid in equilibrium, where gas-liquid equilibrium system here involves multiple components. So this multiple component, previously we have gas-liquid equilibrium, where we have single condensable. But in this part 3, we'll look into gas-liquid in equilibrium where we have multiple components that can condense. Okay? So for multiple components, when we go into multiple components, there are two laws that we will look at, that is Raoult's law and also Henry's law. Raoult's law and Henry's law actually an equation that relates gas phase and also liquid phase. You can see this equation. We have this part is for gas phase, which is in equilibrium in the liquid phase. So this law actually relates the composition in gas phase with the composition in the liquid phase when they are in equilibrium. Same as Henry's law, we will see here this is a part where gas phase composition relates to liquid phase composition. So, what is important about these two laws? Importance about these two laws is when we have, let's say, we know composition of one phase, we can actually if we know one composition of we know composition of one phase which is in equilibrium with another phase, we can actually we know the composition and also the system temperature or pressure. We can actually determine what is the composition of the phase of the other phase that in equilibrium with the phase that we know. So let's say we know this, we know a composition in X, and we know the system temperature. We can actually find what is the pressure and also what is the composition of the component in gas phase, because this part is for gas phase and this part is for the liquid phase which in equilibrium. So these are Raoult's law. We will still use the Raoult's law that we use in single condensable. However, we're going to extend it for multiple component. Okay. And for Raoult's law, if we want to use this equation, so we have to know that the XA, the mass composition of the component, is almost 1. For one particular component is almost 1. And if we want to use Henry's law, which is quite similar to Raoult's law, but we look here, this is the gas phase, equilibrium liquid phase. We see this is still mass composition. This is Henry's law constant for the component. If we want to use Henry's law, we need to know the value for this Henry's law constant. But unfortunately, in our textbook, we do not have this. But let's say if you need to calculate during exam or your test, this value need to be given by the examiners. So, because this value, we do not have it in our textbook. So, this is Henry's law's constant, yeah? And this law applies when our XA is almost 0. So, this is for liquid which is very diluted with this component. Okay? So let's recap what is the importance of these two laws. These two laws is actually relates the composition of both phase. So if we know this phase, composition of this phase, and these two phases are in equilibrium, we can actually determine what is the composition in the liquid phase, and vice versa. Okay, that is the importance of these two laws. Okay, and these two laws now is for multiple component. I'm going to show you how we're going to use Raoult's law for multiple component here to solve for composition in one of the phase. Okay, let's look how we are going to use the Raoult's law and Henry's law just now to solve unknown composition in gas or liquid phase. So we have this question. An equimolar liquid mixture of benzene and toluene is in equilibrium with its vapor at 30 degrees C. Find the system pressure and composition of the vapor phase. Sorry, this is vapor phase, not vapor phases. Vapor phase. Right. So, since if we look at these questions, we are given information about liquid mixture. It says we have equimolar of benzene and toluene. That means in our liquid mixture, the X for benzene B, XB is equal to 0.5. Toluene is also 0.5. So since we are given information about X, so the best way is to use Raoult's law, because we have X, and we have information about benzene and toluene in our textbook. So let's use Raoult's law. Okay, so let's use Raoult's law. So when we look at here, we use Raoult's law because we have information about benzene and toluene in table B4. So for the Antoine equation. So we know to find the system pressure, we know system pressure is a summation of vapor pressure in that system. Okay, so we know our system only contain benzene and toluene. Okay, this is our pressure in this is our system enclosed in a container like this. So we have a liquid which is equimolar of benzene and toluene, and its vapor is saturated with the compound of benzene and toluene, because this system only contains benzene and toluene. It's just that we do not know what is the composition of vapor here once they are in equilibrium. Okay, so we know we can find pressure of the system using partial pressure of B plus partial pressure of T, because this system only contains two component, benzene and toluene. So this is how we find our pressure. To find partial pressure of benzene, we remember partial pressure of benzene is equal to mass fraction of benzene times with the vapor pressure of benzene. Vapor pressure of benzene is calculated using Antoine equation. Okay, so to find benzene here, so you have to go to your textbook, so you know this value, and then you find this value in your textbook, so you obtain the partial pressure of benzene. Partial pressure of benzene here is 59.6198 millimeter mercury. That is for benzene. And then, because to find P, system pressure, we need PT as well. So we have to find the partial pressure for T. So partial pressure T is mass fraction of T, which is also 0.5 because of equimolar, times with the vapor pressure of T at system temperature 30 degrees C. So we have this. This is from Antoine equation. So we obtain the partial pressure of T equivalent to 18.3367. This is yes. So once we do this calculation, we obtain partial pressure of T, which is 18.3367 millimeter mercury. So once we have partial pressure of B and also partial pressure of T, we find the pressure of the system. Pressure of the system, PB, pressure of the system is equal to partial pressure B plus partial pressure T, equivalent to approximately 70 millimeter mercury, 78 millimeter mercury. So we now have already obtained our pressure of the system using this equation from Raoult's law. Now let's find the mole fraction for benzene and toluene in the vapor phase. Now let's find the composition of the vapor phase. Okay, so now vapor phase, not vapor phases, only one vapor phase. Alright, so we know just now we have obtained P of the system from the calculation of partial pressure, so approximately around 78 millimeter mercury. We remember Raoult's law, where we have Y times P, pressure of the system, equivalent to mass fraction times by the vapor pressure of that component. So we utilize that equation. So for now, we find the mole fraction for benzene. Okay, YB is equivalent to mass fraction times by the vapor pressure of benzene at temperature 30 degrees C, because the system is at 30 degrees C, divided by the pressure of the system, which we obtained just now, 78 millimeter mercury. And we do this calculation, so we obtain that fraction of the mole fraction of benzene in the vapor phase is 0.76 mole per mole. That is mole fraction there. Okay, so to obtain toluene, because this system is only contain two compounds, we can either use 1 minus 0.76, or we can do this calculation where we can do that similar to benzene just now. Then we obtain our composition for T equivalent to 0.24 mole per mole. So this is our answer. Okay. This part 3 actually showing how gas liquid equilibrium for multiple component. And so I show you how we use Raoult's law to determine mole fraction for gas phase using Raoult's law. Or the other way around, you can, when you know gas phase composition, you can actually find the information mass composition of liquid phase. Right. Thank you for watching.